Alright, so this is my Boids simulation. Boids is birdoid objects. They follow three simple rules: separation, alignment, cohesion, and then they have a radius that they can see. So say if you set your separation very high, then they don't want to be very close to each other. That's the goal of separation, so they try to avoid each other. Alignment is they try to face the same direction as their neighbors. So everybody who's within their radius, they try to face the same direction as them. And cohesion is how close together they tend to want to be. So if you put your cohesion very high, they flock very close together. And if you put your cohesion very low, they want to spread out. And by combining these three different attributes, you get all sorts of weird behaviors, emergent behaviors. So this simulation is the same as before. We have 500 prey who are green, and we have 5 predators who are red. And they each have different attributes. The prey has a speed of 60, and the predator has a slightly faster speed at 65. So you'll see when prey start moving in, the predators spread out. So the behaviors of the prey, they try to run from predators. The predators try to catch the prey. I don't have anything programmed for what happens when they actually catch them, not yet, but that is a planned, that's further along in the plan. And also one thing of note is that the predators have a higher separation value than the prey, so they don't want to be close to other predators. They don't mind getting nearby, but they don't want to be right up next to them. And also their alignment is actually much lower than the prey. The predators don't tend to really care very much about other predators, but they don't really seem to mind them existing. And this is with 500 prey and 5 predators. Here we have the same simulation, but we added 20 scouts, and scouts have the same 3 rules that the other species have, but they also have rules to get close to predators to kind of shoo them away. And predators have a behavior where if a scout gets within their awareness window, they will turn away. They flee scouts. So they chase prey and they flee scouts. So you see the flocks that have scouts in them aren't really being pestered too much by the predators. And this is an emergent behavior. This just happens. There's the same 3 simple rules: separation, alignment, and cohesion for each species. And then there are interspecies rules. So predators chase prey, predators flee from scouts, and scouts try to match alignment with predators, which causes some fun behavior. Like you can see here, the predators are trying to move in and the scouts are forcing them out. And then their affinity to be around other prey brings them right back into the prey group once the predators have run far enough. And we can see we're getting about 50 frames per second with the awareness rays turned on, which are only for illustration. They actually have a full 360-degree awareness, but just for illustration to save on rendering, because even just this amount of rendering, as you can see, we're getting about 50 frames per second right now. And if I turn off the awareness, we get an extra 10 frames per second. So that's kind of an expensive task, just drawing these lines when we have this whole simulation going. But the awareness rays are toggleable, and the menu is also toggleable. And all of the values are changeable for predator, prey, predator, and scouts. So, like, say for instance, we could make the predators much faster. And you can see all the damage that they cause to the flock, just dispersing the whole thing everywhere they go. And they still get scared away by scouts when they get nearby, but they are really wreaking havoc on the prey here. But if we turn their speed way down so that they're now slower than the prey and slower than the scouts, so now predators are only, say, a 55 pixels per second. The flocks kind of escape them, so like this guy can't quite catch anybody. But say he gets close enough here, he's going to whip in there, they're all going to try to flee, and this is all emergent behavior. Everybody's trying to flee him, and he's trying to chase them, and now they're actually out of his window. So he'll stop chasing anybody and just kind of, with a slight jitter, I added a slight jitter so that nobody stays going perfectly straight for too long. But other than that, like, until somebody gets within their window, and then they start chasing. So let's talk about the program a little bit. I used the SFML set of libraries. It's for C++, and I wrote 2 header files and 3 CPP files. This header and this CPP file kind of aren't really necessary, but it was just so I had an external variable that I could share between Boids CPP and main CPP, because I have part of the logic is in the main loop and part of the logic is in each Boids loop. So let's go over what I've got. So I'm using a parallel grid. The grid breaks the area down so that Boids are only looking nearby for their neighbors, instead of having to calculate for every single other Boid on the entire screen, which was really processor intensive. Now they only have to look at nearby areas. So it takes the size of the window and divides it into a grid, and the grid is 120 pixels by 120 pixels. So it divides the grid, it divides it into a grid, and then they only look into their neighbor areas. Then I also have some variables set up for the menus and whether or not to show the awareness rays. Let's see. These are the default, or not the default, but these are the behaviors that they all spawn with. Max speed, separation, alignment, cohesion, and radius. And each species has their own their own subclass, and that all gets passed in when I create the flock. So for the largest simulation, I did 1,500 prey, 5 predators, and 20 scouts. The highest I've been able to do with even decent frames per second is about maybe about 3,000 Boids total, and I can still get about 40 frames per second. But it took a lot of parallelization of the properties that I could parallelize. This is for debugging. I had the frames per second, and then I also used the FPS to figure out the delta, so that the Boids move on a per second basis instead of on a per frame basis. Because when the simulation got slow, they got slow, and when the simulation got fast, they got lightning fast. I have, let's see, this is where I set up, this turns on and off the menu, and this is using SFML, the keyboard, and then the key is part of that, the enumeration underneath keyboard, and then it has every single key under there. So tab, left shift, right shift, up, down, left, right, add or equal if you push shift, or sorry, equal or add if you were to push shift, and hyphen and subtract, so that I could get this menu to work properly. And basically we've got the species is a group ID, and it's enumerated. I don't remember where I enumerated that, but I was using numbers, and then I decided to make a whole structure for that. And so this is the backside of the menu, and I have, let's see, and this is putting the Boids into their groups. This is passing all of the relevant info. They need that delta time so that they so that they act right. This I use so that we're only looking for the awareness rays. When awareness rays are turned on, it's only near the mouse in a 50 pixel radius around the mouse. When I get to the render frame, it's kind of sloppy. But let's see. This is to just draw all the Boids, which, yeah, it's a fun thing to do. But let's see. So this is if show menu is true, and that's that variable we had before, and we can toggle that with tab. Well, if it's true, then it will display either prey, predator, or scout in the selected species. These are each part of the menu, and if that is selected, then you get bracket, bracket, space. If it's not selected, you just get space, space. So that way it shifts over a little bit. And this is just a background for the menu so that it looks okay. And this is just a population counter, so so I can kind of show off that I'm able to get 1500 Boids running at a decent frame per second. Let's see what the Boid header. These are just the variables that each Boid has, and this is where I did the species enumeration. This is what the Boid class looks like. I've got their location, their x coordinate, y coordinate, their species type, and then their behavior profile. And yeah, this is all fairly common with like Boids, simulations. And then when I actually get into the Boids CPP, things get kind of messy here, also, because this is 276 lines. I probably could have made it cleaner, but well, I didn't. So here we have the Boid class, and it's got the X, Y, the species type, the behavior profile, and with that we pass in the group ID, that's 0, 1, or 2 for the 3 species we've got, and the behavior profile for the whether they are predator, whether they are prey, predator, or scout. This is just drawing them as a triangle. They're 6 pixels tall. Well, from their origin is at 0, so they're 6 pixels tall. Actually, I guess 10 pixels tall and 6 pixels wide. Their color is dependent on their species, which is their group ID. And then the awareness rays are also dependent on their species. And that's, I set that here in its own function, so that depending on which species they are, they get a different color set of awareness rays. This is where the species interactions come in. So this is the prey's interaction, and in the simulation where it was prey and prey, like it was only the greens. This is just standard Boids simulation. It's separation means they want to be further away from the other Boid, and that the amount of further away is based on the distance to the other Boid. The alignment is just make my alignment, add in their alignment. Cohesion is similar to separation, but the distance is not part of that calculation. And then this is to add, if they have another neighbor. So the number of neighbors that they have, all of these numbers get divided by the number of neighbors that they have, and that, sorry, not all of them, but most of them get divided by the number of neighbors that they have. And then predators, working with predators, all the same rules. They want to be, whatever, just a standard amount. And I put in, I was tweaking this, and then I thought that, well, they probably don't want to be okay. So the prey, this is just prey with prey. Prey with a predator, now they want to normally be separated from other prey by a certain amount, whatever this math comes out to. They want to be separated by the same amount from predators 40 times as strongly. So they flee predators. If any predators get nearby, they run. And I don't make any calculation with alignment or cohesion. They don't care which direction the predator's facing. They want to be away from it. Now with scouts, the predator wants to have cohesion with the scouts, and they want to be as close to a scout as if the scout were prey. But they don't try to align or separate from scouts. They do their own thing, but they want to be nearby. Predators, on the other hand, chase. So their cohesion, they try to follow the prey. And, they have just standard rules for themselves. But if a predator sees a scout, they try to flee the scout. So the scout's location, it gets subtracted. And then the scouts, on the other hand, if they want to be nearby, just barely, half as strong, but they want to be nearby to prey. And then scouts with other scouts follow all the normal rules. But then scouts and predators, this is where I got a little bit funky. I added in a little bit of a lead on so the scouts try to go where the predator is headed, and so I got a future vector, which is just the predator's position plus their velocity. So it's, okay, their velocity, half their velocity plus their position is going to be where they are. And then their cohesion, they try to move towards that position. They align, they try to match the others, they try to match the predator's velocity. So they try to swoop in and kind of nudge the predator out of the way. And the nudging kind of just happens naturally because predators flee. They flee scouts, and then they they separate just a little bit because they don't want to actually chase down the predators, but they want to get close to make the predator leave. And I think that's it for Boids CPP. I had another. Oh, it's here in the update loop. Sorry. Here in the update loop, this is where all of that separation, alignment, and cohesion comes into play. This is the wander strength that is, they just barely wiggle every now and then. They just barely wiggle. This is where they are in the cell, so that they're only looking in the neighboring 8 cells in their own to calculate their friends instead of looking across the entire screen. This is where they check for their cell plus the 8 neighbors. I parallelized this next part because it was very resource intensive. I did a toroidal position, so if you drift off the left side of the screen, you pop up on the right side of the screen, and if you drift off the top, you come into the bottom. And distances are calculated that way too. So if they're over here on the left side of the screen, that counts as a neighboring cell, even if their neighbors are over here. And let's see. Yeah, so this is where I pass in the group ID, and that gives them the case of either predator, prey, scout. This is where we average the forces. So we take alignment and divide it by the neighbor count, or we take cohesion and divide it by the neighbor count. And this is where we combine the forces into a steering vector, because some Boids simulations, I didn't like the way that they acted. So in this case, I wanted them to act more like fish or like birds, where they can move forward and they can turn. They can't just stop and they can't strafe. They can move forward and they can turn. And so this is all the math that I had to get together to combine all of that. I used the fast cosine and the fast sine just to save a little extra. And this is the world wrap that I was talking about, where the stuff if they pop off the left side of the screen, they come into the right side of the screen. And yeah, that's the update loop. And the triangle is set to whatever their position is, the xy, or position.x, is their x coordinate, position.y is their y coordinate. This position is a vector too, so it's 2 float values. So it's the x and the y. And their rotation is their orientation in degrees times by 180 degrees divided by pi in degrees. And I think that captured all of the code. The other problem I had with this project was getting the SFML libraries to work with C++. They're designed for C++, but to actually get them all properly included took quite a bit of work. So let's see. Yeah, so we have the SFML include libraries, and we also have linked all the libraries. So the graphics library, the window library, the system library, and the audio library. I never implemented any audio into this project. I haven't implemented it yet, I should say. But something's got to be done. So, and there was also, where were they hiding Well, I also had to turn on OpenMP so that I could get some parallelization going because everything running on one thread just wasn't doing it. Um, so like here's the program running with 1500 Boids, and we can see from the process memory we're only using about just under 60 megabytes of RAM, but I'm using all my processors, every thread of every processor, to get this running as smoothly or as not smoothly as it happens to be. Thank you, and I hope you enjoyed my project.